If you want to, we can talk a little bit about your background. Is that something you're wanting to do or willing to do?
Yeah, sure.
Okay. All right. So, why don't you just tell me a little bit about your background? How did you get to where you are right now?
Yeah, so right, now I'm in my fifth year as a PhD student, and I'm about to graduate this summer. I think, yeah, this probably goes back to I was at undergrad. I think I know, of course, people made up their minds to go to the graduate school or not in their undergrads, and I sort of just got into complexity theory and theory of computation in my first year, even though at that time it was very basic and very vague idea of what's going on in the world with these NP hardness or NP completeness and yeah, P versus NP problem. Oh, like they just sound very fantastic and magical to me. And I took these classes of algorithms and complexity theory when I got into my later years in undergrad. And I also did some summer research at the Cryptographic Center and the Quantum Information Center at the University of Maryland, which the professors there, such as John Katz and Andrew Charles, they inspired me a lot on their research. But even at that time, I would say I hardly really understood quantum at all. I don't know what's going on in the research field. And then I came to grad school, and I came to this quantum group hosted by Scott Harrison at the University of Texas, Austin. And I told him, okay, I think I worked a bit on cryptography as an undergrad. Do you know what's going on with quantum cryptography? And he just gave me a project of quantum copy protection. And he asked me to look into this paper called Quantum Lightning. And by Mark Gentry. And this paper is the paper that I talk about that first attempted this lattice-based quantum money scheme, but failed, of course. And it also instantiated this Oracle-based money scheme that I just mentioned on lattices. This paper, yeah, it took me quite a while to digest the paper because I was in my first year and I didn't know what's like the best way to read and digest the paper. But I found that the topic of quantum copy protection and all these unclonable primitives just very attractive, because one thing is that this demonstrates quantum advantage in a very different way, because people in the quantum computing industry, they talk about quantum advantage every day, but most of the time people care more or say focus on the efficiency side. Okay, we want to say, okay, we know that quantum computers can solve some problems quickly and some others not. And we just want to find out more problems that we can solve quickly, much faster than a classical computer on a quantum computer. But I think this is not the only advantage quantum computers can do, because it's not just quantum algorithms that makes it different. Quantum information itself makes quantum computers different, because there's advantages that it can take use of quantum information itself when you just compare to the classical information. So there's all these cryptographic protocols that's built upon the power of unclonability of quantum information. It's simply another demonstration of quantum advantage. And from another point of view, even though it's not about efficiency, but it demonstrates something that's completely unrealizable, a security property that's completely different from what people have been doing with classical cryptographic protocols. And yeah, I simply find that amazing. And I think efficiency is probably, it shouldn't be the only focus in quantum research, in research towards quantum advantage and in research towards quantum capabilities. Security is also important. And it's not, yeah, people usually think efficiency is more important. I think especially for the industrial and practical side, but yeah, people would realize that security is just as important as efficiency when there are security problems that come out. Yeah, people, yeah, usually industry only realizes that when there are security issues that come out. and they just try to fix the bugs and make up for things. But that demonstrates that at the very end of the day, security is just as important as efficiency, and we want more security guarantee in our day-to-day life. And even the quantum copy protection and quantum money is still, a bit away from being practical nowadays. But I wouldn't say it's that far away. Nowadays, we have seen that there's already experiments for quantum key distribution. And so if we have certain schemes where we take use of these quantum money states, but they're not like highly entangled as some of these recent schemes we put forward. They could be Wisner states, conjugate coding with some modification, and they can already be used using a lot of protocols, such as QKD and private key quantum money and position verification. And in some settings, they can be used. In some settings, there's like a weaker version. There's some weaker version of quantum copy protection, where you have to show that you have deleted a certain software after using it. And in that case, sometimes you can use easier money states, and you can have easier to prepare money states, and you can have more lightweight cryptography schemes. And yeah, I do think these things would become practical someday, and they are not simply stories that we try to make up in our papers. All right, and also I certainly find like on the way to studying all these things, I have to learn both about quantum information and the classical cryptography, and that was a lot to learn, and I'm still learning, because there's really a lot of stuff out there, and I simply find, well, both of these communities both of the studies and the communities of the quantum information scientists and the communities of the cryptographers, they probably they value different problems, they study things from different perspectives, but both of them are quite attractive and interesting.
Okay, excellent.
Yeah. Okay. Yeah, I think that's basically my thoughts over the past few years as a grad student. Right.
Okay, so another interesting question is, how do you work? How do you work as a mathematician? I mean, I read somebody saying he always thought his dad, whose father was a mathematician, he thought his father, or he thought math was something that you did on the front porch, right? Because that's where his father would work, right? So how do you do mathematics?
Oh yeah, I wouldn't say I'm a mathematician, because I feel like what I do is slightly less hardcore than what real mathematicians do. But we do use a lot of mathematics. I think what you said is exactly right. I feel like a lot of times we work not actually, even though I would say I consider myself a computer scientist, but a lot of the time I don't work on computers. I just work, for example, doing housework. I work when walking to the supermarket. I think about a lot of things, especially like these abstracted cryptography protocols, where I have to figure out the high level intuition first. I don't have to write down the math like when I begin, and I just think about things when I'm taking a walk outside. And I think this is really nice, because it occupies a lot of free time of mine, but it's saving time in some sense, because I don't have to stick here to my desk and sit every day. And a lot of times I think about this high level intuition, and when I feel like, okay, I think I'm 90% or even 70% sure that this is working, and I go back to my desk and do some computation. I think this is basically how we work, and also another thing is, of course, reading. I think reading papers. I think this is very important in cryptography and in theoretical computer science in general. Yeah, I guess for more hardcore mathematics, of course, I think a lot of things are built on, a lot of things are built upon past ideas. Of course, this is with all research. But especially I think with cryptography and every day there's like a lot of new papers coming out, and especially with quantum cryptography, you sort of have to catch up with these new techniques out there and these new directions. Yeah, like back in probably a few more years ago, like before before I started my PhD, I think at that time, quantum cryptography wasn't much of a big deal besides these experiments on quantum key distribution. When people mention quantum cryptography, they probably only think of quantum key distribution, and they would ask, okay, what else is there? But after a few years, there's been a few experts, they have been working on like these unclonable primitives. They conjecture like things that they build things that's not realizable by like classical cryptography, and they also put forward the idea that, okay, we have to analyze quantum, we have to analyze classical cryptography protocols, even though they are not built on discrete law or factoring. We have to analyze them in a quantum way, and here are a few methods and techniques to analyze them, in order to guarantee that they are secure in a quantum world. And they put forward these ideas out there, and gradually the community was expanding, and nowadays, like every day, there's new quantum cryptography paper coming out, and I think I sort of had my PhD in an age where this community of quantum cryptographers is like, yeah, thriving and expecting, and I sort of experienced a good time to go into the research in this field. And I would say, yeah, but one bad thing about this is that we have to keep track of new things coming out every day, and have to learn a lot of different things people have been using and put forward, right?
Okay, that's great. All right, well, I think that's wonderful, and I'd like to thank you again for doing this.